Are you looking for a good probability question that could possibly be on the AP Stats exam this year? Well, you've come to the right video. This is the 2018 FRQ exam for AP Statistics, question number 3, full answers explained. A fantastic probability question. It's got a little bit of easy parts, a little bit of tough parts, but I think you'll like it. All right, so here's the question. Approximately 3.5% of all children born in a certain region are from multiple births. Twins, triplets, etc. Obviously anything more than a single birth. Of the children born in the region who are from multiple births, 22% are left-handed. Of the children born in the region who are from single births, 11% are left-handed. So we got two things going on here. Left or right-handed, or are you born from a single birth or from multiple birth? Now there are 3 questions and we're going to tackle each one at a time. But before we even read the questions, I want to first notice that these probabilities here are conditional. See, the 22% is the probability of being left-handed on the condition you came from a multiple birth. The 11% chance of being left-handed is on the condition you came from a single birth. So to even get to that 22%, you have to first be from a multiple birth. And to even get to that 11%, you have to be from a single birth. So this is a great, fantastic opportunity for a tree diagram. And in fact, that's exactly how I'm going to solve this problem, is by using a tree diagram. So let's specifically look at question A. What is the probability that a randomly selected child born in the region is left-handed? And this is exactly why a tree diagram is going to be really helpful here, because there's 2 ways you can be left-handed. You could be left-handed from a multiple birth, or you could be left-handed from a single birth. And I know that they are not independent of each other from the pure fact that I know you're more likely to be left-handed if you come from that multiple birth versus less likely to be left-handed if you come from a single birth. So let's start off with making the tree diagram, because it's going to make answering this question really easy. So here is that region of the country, or whatever it said, specific region. And from this region, 0.035 is the chance that you come from a multiple birth. I'll use MB there for multiple birth. That means all other births are from single births. So 1 minus 0.035, this would be all others. This would be the 0.965 that must be a single birth. So I'll use an SB there for single birth. Now, of those kids born in a multiple birth, there is a 22% chance that they are left-handed, which means there's a 78% chance they are right-handed, which I guess would be the opposite of left-handed. Of those born in a single birth, 11% chance they are left-handed, which would mean 89% chance they are right-handed. So again, we see that 2 branches lead to being left-handed. Left-handed coming from a multiple birth, left-handed coming from a single birth. So all I have to do is multiply to figure out each of those branches and then add them together, because only one of them can happen. So I'm either going to come from a multiple birth and then be left-handed, or I'm going to come from a single birth and then be left-handed. That's going to get the probability that a person from this region is left-handed. We're going to go ahead and grab my calculator here. All right, so 0.035 times 0.22 plus, an extra 2 there, I'm sorry about that, plus 0.965 times, minus, having a hard time here, times 0.11. Double check that work, 0.035 times 0.22 plus 0.965 times 0.11, and we get 0.11385. 0.11385. We'll get a lot of kids say, well, can I round that? I mean, sure, knock your socks off, but why not use all the decimals if this is the official AP Stats test and you want to get a great grade? So there is the probability that a person born in this region is left-handed. All right, part B. What is the probability that a randomly selected child born in the region is a child from multiple birth, given that the child is left-handed? So I see that word given, which is an instant sign I'm working with a conditional probability. So when we write a conditional probability, we use our little P for probability, then we put a line in the parentheses. After the line is the condition, in front of the line is what we're looking for the probability of. So let's make sure we don't get these mixed up. So the question literally says, what is the probability that a randomly selected child is from a multiple birth? So that's what they actually want us to find the probability of, but they're not just stopping there. If they stop there, that'd be easy, 3.5%. But it says specifically given that they are left-handed. So now I have to find this probability. Now to do this, I'm going to use the conditional probability formula, which is a really simple formula that is on the AP Stats formula sheet. It's the probability of both events, multiple birth and, that's our symbol for and right there, that upside down U, and left-handed, divided by the probability of being left-handed, just straight up left-handed. All right, now here's the good news. If you paid attention to what we did in part A, we have already calculated the probability that a person born in this region is left-handed, which is going to be my denominator, 0.11, let me just make sure I have it right, 0.11385. Now, the numerator is very specific. It's multiple birth and left-handed. So I go back to my tree diagram. That would only be this top branch. This top branch right here is the specific branch that is only for multiple birth and left-handed. That branch is 0.035 times 0.22. So that's going to go on my numerator here. 0.035 multiplied by 0.22. So again, conditional probability, the numerator is both of the items, so multiple birth and being left-handed, which is a very specific branch. The denominator is just the condition or just the given, which is left-handed, which again, we already calculated. So now I just got to go ahead and put all of that together on my calculator. 0.2, well, let's start that again. 0.035 times 0.22, that's the numerator, divided by the 0.11385. And this is going to get me my conditional probability. And it is 0.0676. 0.0676. Easy, awesome, fantastic. All right, now for part C. A random sample of 20 children born in the region will be selected. Okay, so I'm going to look at a very specific sample of 20 random children. What is the probability that the sample will have at least 3 children who are left-handed? So I'm looking for X, the number of left-handed children, to be greater than or equal to 3. That's what at least 3 means. So I got 20 kids. I'm looking for 3 or more of them. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, or all 20 of them to be left-handed. Now, the only other piece of information I need to answer this question is I need to figure out the probability of being left-handed. What is the probability that a person is left-handed from this region? Oh my gosh, once again, I already answered that all the way back in problem A, so that's 0.11385. So this is a binomial distribution. Why? Because I was given a specific number of trials, in this case 20 people, and I was given, but I actually kind of found it on my own, the probability of success. I'm looking for left-handed, so anytime I find a left-handed person, I'm going to be success. That's what makes this binomial. Now, we do have to have independence, which means that what happens to one person being left-handed is not going to impact the next. So it's not like it's not like it's a contagious disease. I can rub my left-handedness off to somebody else. And I do have to have every person either being left-handed or not left-handed, and that makes a lot of sense. Those are the only 2 options there. So this is a binomial distribution. And I'm looking for 3 or more. Now, if you remember the binomial distribution, to calculate probabilities, it involves 3 parts. So let's start with 3, because it does say 3 or more, so eventually I'm going to have to figure out the probability of 3. So the probability of 3 left-handed people, well, that means I need 0.11385 to the third, because I need 3 people to have that probability of being left-handed. And then the opposite of that is how many people I would need to not be left-handed. So that would be 17 people that are not left-handed. Now let me figure out that probability. So I'm just going to do 1 minus 0.11385. And, an extra 1 there. This calculator is sticky. Okay, there it is, 0.11385. So that is 0.88615. 0.88615. Now, so this is the number of successes I have. This is the number of failures I have. And the remaining part is out in front is how many different ways I could have 20 people and 3 of them be my left-handed. So if you think about these 20 people in a line, the first 3 could be my left-handed people, the middle 3, the last 3, the first 1 and the last 2. I mean, there's lots of options for how many that could be. Now, a couple different ways I could get this answer on my calculator. One way is I could do it step by step. So the first step is figuring out how many different ways you could have 3 people successful out of 20. So what you're going to do is you're actually going to type in the 20 first, Then you're going to hit math on your calculator, slide over to PRB for probability, and choose the NCR. This is going to figure out how many different combinations there are. 20 people, choose 3 of them. And this is 1140. So there's 1,140 different ways you could have 3 left-handed people in a group of 20. So I'm going to take that 1140. I'm going to multiply it by the 0.11385 raised to the 3rd. And then I'm going to multiply that by 0.88615 raised to the 17th, because if I got 3 people that are left-handed, I got 17 people that are not. And there is the probability, 0.2155, that I have 3 left-handed people. But the problem is, I'm not even close to being done, because it says at least 3, which means 3 or more. So now I have to do exactly what I just did for 4, 5, 6, 7, 8, 9, 10, all the way to 20. And you might be thinking, boy, that sounds like a lot of work. There's got to be an easier way. There is. Another way that you could tackle this is to find the probability of what you don't want. I don't want 0, 1, or 2 children to be left-handed. I'm looking for 3 or more. What I'm not looking for is 0, 1, and 2. So if I tackle this by looking at 1 minus the probability of 0 plus the probability of 1 plus the probability of 2, and I get rid of that. So I find the 3 things I don't want and then do 1 minus that result, I'm going to be left with the probability of what I am looking for, which is 3 or more. So let me just show you that work a little bit neater. So here is that exact work. So 20 choose 0, 0 people left-handed. All 20 are not right-handed. That's the 0.88615. Then here I have 1 person that's left-handed, 19 that are not. Here's the 2 people that are left-handed, 18 that are not. And remember, these first parts here is simply calculating how many different ways this can happen. Once I get those probabilities, I have to subtract each of them away from 1, because if I get rid of the 3 things I don't want, I'm going to be left with what I do want, which is 3 or more. So the final answer is 0.402. So the probability of 0, 1, and 2 is 0.598. 1 minus that is going to leave me with my final answer of 0.402. Now, a couple different ways to get this easier on your calculator. Now, other than doing it by hand, which is what I just did, I mean, the calculator did the math, but I had to type everything in. There's this really cool feature called second vars. Under second vars, you can scroll up to binomial PDF. This will do all of the math for you. All you're going to do is type in 20 trials. The probability of success is 0.11385. And X is how many you're looking for. So for example, in the problem I did with you, I was looking for 3 people to be left-handed. Look how fast that gets to the same answer of 0.2155. So what I can do is I could go second vars, and I could do a binomial PDF, and I could do 0, I could do 1, I could get 2, write down those 3 separate answers, and then subtract each of them away from 1. That way I'm left with everything else, which is 3 or more. Or another cool thing you could do is use binomial CDF. Now what binomial CDF does is it's really cool. It's just like binomial PDF. The only difference is it says CDF. 20 trials, 20 people. Probability of success, 0.11385. Now if I type in a 2 here, it's going to calculate the number I type in and anything less. So this is going to actually combine 2, 1, and 0. It doesn't go up, it goes down. So if I type in 2, it's going to spit back not only 2, but 2, 1, and 0. So this is going to get me that 0.598 number. That is the probability of 0, 1, or 2 left-handed people. But remember, that's not what I'm looking for. I'm looking for the opposite of that, which is 3 or more. So if I do 1 minus that value, I get the 0.402. Easy, I hope. Hopefully part 1 and part 2, or A and B, were pretty simple. I hope you'd agree on that. Part C is a little bit complicated. You do have to remember what a binomial distribution is and how to use it properly. But with a little bit of, memory there, hopefully it wouldn't be too bad. All right, that's it for this video. Can't wait to see you in the next one.